Hi everyone. Today I'm going to talk about some fundamentals of high-performance interconnects for AI. In this discussion, I'll be giving you my own viewpoints, not the viewpoints of my employer, Microsoft. So it's almost cliche to say that AI is causing disruption. The compute demand has gone up by a factor of 4 in the last 2 years, and it doesn't show any signs of slowing down. And the only precedent I can think of is the internet bandwidth growth by the same factor between 1996 and 1999, and I was right in the middle of that tornado. Hyperparallelism in AI means that interconnects are central to the problem, not peripheral. As an example, just comparing GPU bandwidth to CPU bandwidth, it's 100 times greater. Also, the workload for AI is different than standard general-purpose workloads for VMs, for example, which means that the trade-offs that we need to make are different. But overall, performance, power, scale, and reliability will trump features in this new problem. But hard problems that happened in general-purpose networks are even more difficult here. So there's a need for new solutions. Now, when you're in the middle of a tornado, it's very easy to get lost. And as the picture shows, you need to be grounded. And therefore, one of the things I'm going to do in this talk is actually ground us on some fundamentals of interconnects. Now, interconnects are a complex and multidimensional problem. And why is that? Well, there's 3 dimensions of an interconnect. One of them is the topology, the other is the physical layer, the third one is the logical layer. But for this problem, for AI, we're talking about some 7 different bandwidth latency domains. What I will be focusing on, given the limited time, is only 2 of these bandwidth latency domains. One of them is called scale out, the other one is called scale up. And for each of these domains, we're going to cover the 3 dimensions in some detail in the next few slides. So talking about the fundamentals of topology, this topic has been covered extensively in the literature over the last 30, maybe 40 years in the context of high-performance computing. Most of this work has been academic, and it's been focused on low-radix switches. Many of these topologies are non-isomorphic under failure, meaning the topology looks different after failures compared to before the failure. Many of the algorithms that have been suggested here are too complicated for practical implementation. In practice, it turns out that flat, high-radix, any-to-any topologies win. They're easy to implement. They are, most importantly, isomorphic under failure. So, for example, when a link or a switch or a GPU fails, the topology after a failure looks the same as the topology before a failure, except you have less bandwidth. Now, of course, if you provision enough number of paths, that is not a big problem. There are also simple solutions to hard problems like congestion and errors. And we can make these paths have equal and low latency as well as low jitter. And finally, 2 switching tiers are sufficient for 99.9% of the cases, especially with the high-capacity switches that are going to be coming over the next 2 to 4 years. Now let's look at the topologies for the scale-up part of the network. I've shown 2 topologies, one called split, the other unified. I'm going to be focusing on the split network, where the network for scale-up is completely isolated from the network for scale-out. And we'll see this isolation in the next slide. But roughly speaking, based on topology and the capacity of switches, you can support about 256 GPUs. But as we'll see in the physical layer, the physical layer places a constraint that constrains us to somewhere between 50 to 100 GPUs per rack. Let's now look at the scale-out topology. You'll see that here you've got these pods, multiple pods. Each pod is defined by the fact that the GPUs in the pod are connected using the scale-up part of the network, which is shown above the N GPUs in each pod. And the scale-out portion is shown below. And as you can see, the scale-out portion consists of 2 tiers of switches, and none of these switches is oversubscribed. If you run through the calculations, you can see that the total number of switches with 100 terabit per second switches will support about 130,000 GPUs. And of course, with 200 terabit per second switches, you'll double that number and so on. Now in this, it's quite important to point out that the ratio of the scale-out bandwidth to the scale-up bandwidth is assumed to be roughly an order of magnitude, a factor of 8 precisely on this slide. Moving on to the physical layer fundamentals, there are 2 pieces which are important. One is the transmission medium, the properties of the medium. And here the bandwidth distance product of the medium plays out. As you can see, there are 5 curves here. The first 2 curves on the left represent copper. And you can see that copper's gain, the bandwidth drops off very quickly with distance. The x-axis is logarithmic, whereas optical technologies go much, much further, which should be no surprise. But what's important to point out is that there's a large technology gap somewhere between 4 meters and about 20 meters. And that gap absolutely needs to be solved. The second limitation at the physical layer is a limitation imposed by transistors because, of course, signals start out as electrical and they end up as electrical. So transistors have to do the modulation onto whatever medium you use. And practically speaking, that modulation rate is limited to about 200 gigabits per second. Yes, people have talked about higher rates, but it becomes increasingly complicated because of the limitations of transistors and because of limitations of power, more importantly. Some of the metrics that are important at the physical layer are the power per unit bandwidth, cost per unit bandwidth, the distance you can cover, and the bandwidth density, the bit error rate, reliability, etc. Now, the benchmark here is copper. If for some reason we could find a technology that gives you the attributes of copper, but provides you, let's say, somewhere between 10 to 20 meters, I would consider that problem solved. But we're not there yet. So the speed for less than 20 meters, there's modulation rates of all the way from 50 to 100 gigabits per second per lane. For distances above 20 meters where you're doing optical, it's all 200 gig. Moving on to the logical layer, if you focus on the picture on the right-hand side, what you see is a range of semantics, all the way at the bottom where you have small scale, very, very tightly coupled, to large scale, loosely coupled. So you're going from memory semantics at the bottom, which are typically used in high-performance compute, to network semantics at the top. It turns out that for AI computations, we're talking about things which are somewhere in between these 2 semantic models. So distributed memory, for example, which is very close to the semantics of memory, except for cache coherency. And then you have RDMA. And then above that, you have semantics like RPC and TCP, which are also useful in these computations. But across all of these, there are some principles that are important to underline. One of them is the end-to-end principle, which is a simple core and a complex edge. Bandwidth conservation, because it's not possible to manufacture bandwidth. Low latency, and even more importantly, low jitter. Why low jitter? Because this computation is inherently a pipeline that spreads from GPUs across the interconnect to other GPUs. And so if you have high jitter, then your GPUs are going to run at low efficiency. It's also important, very, very important, to not oversubscribe networks because it just makes problems which are difficult even harder. It's important to maintain simple mechanisms which are not overlapping. And finally, it's important conceptually to not confuse host APIs with network transport. For example, confusing the fact that people are using queue pairs as the host interface with the use of Rocky V2, which is a transport protocol. And we should not mix data plane concepts with control plane concepts because they are independent. One operates at the scale of tens of nanoseconds, the other at the scale of milliseconds. So confusing them just leads to bad design. Here is a straw man architecture based on some of these fundamentals. You got a host Q-pair interface, which is, in my opinion, the right interface because it allows asynchrony, it allows lots of parallelism. Then you've got the protocols and the protocol stack on the right. A reasonable stack is some form of simplified Ethernet underneath, where, for example, you're not using Ethernet cosmetically, where every switch is first discarding the Ethernet, first slapping on an Ethernet header, then discarding it at every hop. Doesn't quite make sense. So you can use Ethernet itself to do forwarding, which may seem radical, but actually will afford a lot of simplification. And there are some proposals that are coming out. For example, the SU proposal from Broadcom, which actually try to go in this direction, which is a good direction in my opinion. Right above that is this reliable packet transport layer, which is a fundamentally important layer, which is missing from the TCP/IP suite of protocols. You can build on top of this reliable packet transport layer, RDMA, you can build TCP, and of course, the TCP semantics can be greatly simplified if you have such a layer. And of course, you can do things like RPC, where you can have single packet reliability. Let's now look at a strawman implementation of that architecture picture that I just showed you. And let's look at the various attributes across the scale-up and scale-out networks. So for the scale of the scale-up network, it's about 4K endpoints and a single layer of switches. For the scale-out, it's somewhere between 128K to 256K GPUs, and there's 2 tiers of switches using the topology that I showed you a couple of slides ago. The base protocol for scale-up is as simple as it can be. It's some form of simplified Ethernet. For scale-out, we can afford to have standard Ethernet because it may give you more capability. In terms of packet ordering, for scale-up, we should only order exactly those packets that need to be ordered. For example, the synchronization packets used in RDMA. And for scale-out, you can have both kinds of semantics, either loose or strict. For RDMA, for scale-up, we should implement the minimum necessary semantics. For example, RDMA writes alone are probably sufficient to solve the problem. But for scale-out, you might need more full semantics. In terms of other protocols, there's probably no need in the scale-up network, at least visible today. Even though people are trying to provide memory semantics, for example, a pooled memory in the scale-up network, other semantics might be interesting, but that remains to be seen. And for scale-out networks, it would be profitable, I think, to enable other protocols like TCP and RPC. Now, this base layer that I talked about, which is very, very important, the reliable packet protocol layer, it uses packet spray with equal loading in terms of bandwidth across all possible paths. And remember, the key thing about those high radix networks is the existence of multiple paths, all of which have the same zero load latency because the topology is regular. This reliable packet protocol suggested here uses receiver-based congestion control because that's the natural place to put this congestion control, not at the sender. And it also uses timeouts as the only mechanism for detecting failures of all kinds, both transient and permanent. Now, the recovery from these failures, if it's a transient failure, you just use packet retries. If it's a permanent failure, you remove the path that was failed. And of course, you'll end up with slightly less bandwidth. But as I mentioned earlier, this is not a problem when the number of paths is large. So this is a strawman implementation. Let's take a look now at some of the results of implementing this kind of protocol. So this is an example of a protocol that we implemented at Fungible, which was an independent company prior to Microsoft buying it. What this shows as implementation in silicon of this style of protocol. And there are 3 different traffic patterns that are shown here. A 1:1 pattern, which is completely innocuous and easy because there's no incast. And on the extreme right, you have an incast, which is a difficult problem to handle because of congestion at the receiver. And in the middle, you've got this random pattern. And you can see for all three of these, you're operating more than 90% utilization of the bandwidth in the network. And very importantly, the latency is minimized and the jitter is tiny. Tiny meaning somewhere between 100 and 300 nanoseconds. This kind of jitter is unheard of. And it's very, very important because it will enable GPUs to run much more efficiently. So finally, in concluding, AI represents a new, different, highly parallelizable workload. And in this workload, performance, power, scale, and reliability are the imperatives, not bells and whistles as they were in general purpose computing. And these new imperatives, they force a re-examination of the trade-offs we made in networking in the past. And this re-examination, our only guide is fundamental principles, some of which I've tried to point out. What we need to do above all is get rid of the complexity and the baggage that we carry from the past. We need to be focused on the workload. And we need to be focused on bottoms-up development. It's implementation of some of these simple concepts that needs to drive standards, not the other way around. And to take a page out of what Dave Clark said many, many moons ago about TCP/IP, protocols were developed first, implemented first, and then standardized, not the other way around. So no kings and committees, just implementations. Thank you very much.